Good evening. I'm Eric Isaacs, president of Carnegie Institution for Science. And tonight we're in for a real treat. It is really my pleasure to introduce a Carnegie scientist, Rebecca Bernstein, who's also the chief scientist for the Giant Magellan Telescope, which is what you see up here. I think everyone has been very carefully watching what's been coming out of the sky most recently by looking. It's all over. It's above the fold in the New York Times and the Washington Post. These amazing images that are coming out of the James Webb Space Telescope. And that telescope has produced already things that we had no idea we were going to find. It's just been amazing by looking at everything from young stars just forming inside of these huge nebula where we couldn't see before, to discovering that we have 5 times more galaxies than we ever thought. So we're sending all of our astrophysicists back to the drawing board to figure out what's actually going on. But what we're here to talk about tonight, and I know Rebecca will talk about the James Webb, is really something a project that we've been working on at Carnegie with 12 other partners for well over a decade now. It actually started with us. It's called the Giant Magellan Telescope. And the project here is to build one of the world's largest telescopes, ground-based telescopes, called the Giant Magellan in the Atacama Desert. So Carnegie has had an observatory since the late 60s in Chile, high desert. And the reason it's a great place, and I'm sure Rick will say more, I'll just mention it, is it's one of the driest places on Earth. Many clear nights. And one other little piece of the ingredient is that the air that flows over that particular part of the Earth is very smooth. It comes off the Pacific and it flows over the coastal range and it's very smooth. So it's perfect for seeing. We've been trying to build this or looking to build this telescope for, what is it now, 15 years, 20 years?
Closer to 20.
20 years. But these projects take a long time. The beauty of this telescope is it's on the Earth, which is great. So astronomers can access it. They can make changes and add instruments to improve instruments. Just to see, that the James Webb is phenomenal, and there's nothing that's going to be like it for a while. But once the Giant Magellan Telescope is built, we'll have a resolution that's at least 4 or 5 times better, looking, say, at exoplanets. We'll have a collecting power that's 10 times better than the James Webb. And the Giant Magellan Telescope will be at least 200 times better than anything else we have on the surface of the Earth. And you'll hear a lot more about that from Rebecca. So before I ask her to come up, I just want to give her a little of her history. Rebecca, it turns out Rebecca is a physicist by training, as I am. She got her her bachelor's in physics from Princeton, yep, and then a PhD from Caltech, which is actually where the headquarters for the GMT is in Pasadena now. But she spent a little time at some university, Michigan. She got tenure at Michigan. As soon as she got tenure at Michigan, she moved. She went to Santa Cruz. Santa Cruz, by the way, is probably one of the best universities. A lot of people don't know it. One of the best universities in the country, in the world, for astronomy. So it was a good move. But even a better move she made after about 12 years out of school, she came to Carnegie and she decided she'd make her career as a Carnegie astronomer. And she got caught up in this little project, which, as she said, it was almost 20 years now. She got caught up in a little project called the Giant Magellan Telescope. And what she's here today to tell us about is her vision for this instrument, what it'll do, and how incredible this instrument will actually be. So, Rebecca, please join me in welcoming Rebecca.
Thank you so much. Is this live? It is. Okay. Okay. Well, it's really a pleasure to be here. Thank you, Eric, for that perfect introduction. Everything you said about the observatories in Chile, about JWST, we're going to hear more about all of that. And in this talk, I want to introduce you to GMT, and I want to start by telling you why I think this project is so important. I've been working on it for 20 years in my life, give or take, with a little gap there while I was at Santa Cruz, but I started working on it in Michigan. I've been working on it since I've been at Carnegie. And I do think it's incredibly important. So for me, the reason that it's so important really comes down to 2 things. One is the importance for astronomy, which we'll get to much more in a minute, but the other is the importance for humanity in a much broader sense. This is the sky over Las Campanas Observatory in Chile, where Carnegie's current observatories are. Oh, that's terrific. Thank you. And this is where GMT will be built, right next to Carnegie's existing observatories. And every time I look at the sky there, I find it humbling and awe-inspiring. And I don't think I'm alone. And in fact, there's very good evidence that I'm not alone. These are cave drawings, and they're not just drawings of animals. They are, in fact, star maps that were made more than 15,000 years ago. And we can guess what they might have been used for, tracking time or marking seasons. But one thing they very clearly show is that people were interested and curious about the universe around them. And I have to say, even more amazing to me than these 15,000-year-old star maps is this. The amazing, wonderful attention that JWST has gotten since its launch, as Eric was saying, above the fold in newspapers around the world. Many discoveries from LIGO, from other astrophysical science results have been published above the fold in similar papers. And I think it's wonderful, partly because at this time in our history, particularly in the United States, we need things that inspire us as human beings and can inspire the next generation of scientists to become scientists, and also can bring us together. So particularly with JWST just launched and working so well, I want to tell you why we need a next generation of extremely large telescopes, what we call ELTs, the next generation of ground-based telescopes. And to answer that question, let's start here. This plot shows the increasing size of telescopes over time. So we've got the aperture of the primary mirror, aperture diameter on the vertical axis and time on the bottom. And this plot really is going to illustrate, as I talk my way through it, that each step in collecting area has led to a giant leap in sensitivity, and with that leap, a leap in our understanding of the universe. So with the first telescopes, in the first, say, 100 years of pointing telescopes at the sky, we learned about the solar system. We saw moons around planets, we saw planets orbiting the sun, and eventually we learned about gravity. Then we put our sun into context as one of many stars in the galaxy. And we learned about stars beyond our solar system. And then in the last century, we've come to understand the nuclear physics that powers the sun. We've learned about the universe beyond our galaxy and other galaxies. We've learned that, in fact, the universe is dominated by matter that we do not understand. So we call that matter dark matter. And even more puzzling, we've learned that the universe is not just expanding, but it's accelerating in its expansion, which can only be explained by physics that we don't understand. And so we describe that phenomenon as dark energy. And a little closer to home, we've discovered that there are many planets. In fact, there are planets around nearly every sun in our galaxy, every star in our galaxy. So with the next generation of telescopes, we have many new mysteries to unravel, from new physics that we'll undoubtedly learn, explaining some of these mysteries, and perhaps discovering new worlds. So it is not an exaggeration to say that GMT will really revolutionize our understanding of the universe. It will be able to study everything from the formation of the first stars and galaxies in the universe to helping to solve the mysteries of dark matter and dark energy. It'll help us understand the evolution of galaxies, including our own Milky Way, and particularly how galaxies co-evolve with black holes. It'll help us understand the birth and death of stars and the physics of those black holes that we see forming at stellar masses. And finally, it'll tell us about extrasolar planets and perhaps be successful in the search for life beyond our solar system. So every decade, the National Academy of Sciences convenes a committee to prioritize the problems that are facing astronomy and prioritize what projects are needed to attack those problems. It's called the Decadal Review Committee on Astronomy and Astrophysics. It involves hundreds of astronomers from around our community. In the last 3 years, we've joined forces with one of the other large telescope projects in the United States called the TMT project, 30-meter telescope, to present the science case for GMT and to the rest of our peers in the United States and to the whole US community. And I can't put it any better than they did in their report when they said that GMT and TMT will address nearly every important science question across all of our priority science areas. They are essential for keeping the US community's global scientific leadership, providing important synergistic capabilities that complement those planned for the European ELT. And to that, I would just add that astronomy has impact far beyond astronomy, from physics to chemistry, biology, climatology, and even more important, I think right now, it has tremendous potential for science education because it engages and excites so many people. And so I think the National Science Board really nailed it when they said that for the US to remain a global leader in innovation, not just astronomy, but innovation in science, America's researchers must have access to scientific facilities that will astonish the world, tools that will let them see further, faster, and deeper. So when I see the response that we've gotten from our community, from the National Science Board, I think we've really gotten our marching orders. We need to get this telescope built. So now, with that in mind, I want to show you what we're building. This movie is going to introduce you to the site itself. You see some support facilities coming up on the left, and you see us arriving at the summit now. You see the enclosure. You see louvers opening that allow wind to pass through the enclosure during the night so that it can equalize the temperature and you don't get turbulence inside the dome. You see the dome rotating now that it's open so that the telescope can see out and point to any location in the sky. You can see a truck driving up the side there to give you a sense of scale. And now you're looking at the telescope itself. 7 large primary mirrors, and you can see in yellow a secondary mirror. I'm going to explain what that does in a minute. I'm going to show you a still of the observatory so that you can get a better sense, and just stop for a minute and look at the enclosure itself, some support buildings off to the left. We call those house utilities like water, power, cryogenic systems. We keep those away from the telescope, from the summit, so that they don't add heat to the environment or vibrations. And then over on the left, you see, on the right, you see a support building where the mirrors are going to be treated and cleaned and recoated. And then we'll have nothing else on the summit. Those offices that you see there are temporary. And I'm giving you a good look at this. So you see Las Campanas Observatory and the existing telescopes off in the background there. And now, watch closely as I flip the slide, you're going to see what the summit looks like now. So you can see that we are in process of building this telescope. You can see the foundation ring dug. The hard rock excavation has been completed for the foundation for the ring wall of the enclosure. You can see the central area where the telescope will mount to the bedrock of the mountain. And you can see a utility tunnel coming off to where the utilities building will be. Even when you look at it like this, I can point out as many cars as I want. It's really hard to get a sense of scale. So I'm going to show you the enclosure near in the middle of a more familiar object. This is a 100,000 person stadium. It's the Rose Bowl in Pasadena. And from this, you begin to get a sense of how enormous the enclosure itself is. It's a 22-story rotating building. And the telescope itself inside is 15 stories or about 48 meters tall. Looking at it here, you can get a better view of the telescope. You see the cement pier that attaches directly to bedrock, and the telescope mounts on top of that. In purple, you see the structure of the telescope that supports the primary mirrors. And in blue in the background, you see the inside of the enclosure. This gives you a better view of the telescope itself. It's an optical infrared telescope, so it works at wavelengths from the visible and the atmospheric cutoff at about 0.3 microns, far bluer than we can see with our own eyes, far up into the infrared and the mid-infrared. The primary mirror itself is about 25 meters in diameter from edge to edge, and you can get a better look at it here. Those are 8.4 meter individual segments. They're the largest mirrors ever made, and the accuracy of each surface is about 10 nanometers, which is about 1/1000th the thickness of a human hair. Each one weighs about 18 metric tons, so they have to be supported very carefully, because when you have a mirror of that mass and the telescope points around the sky, it can warp under its own weight. So the support structure is something I'll show you later. And you can see the JWST mirror for comparison, and the little person down there who's probably much taller than I am. Okay, so this next generation of telescopes is about sensitivity, which translates to collecting, which comes directly out of the collecting area. If you can collect more light, you can see more fainter objects. But it's also about resolution. And to separate the effect of those two things out, I'm going to first show you just what it means to get more sensitive, to collect more light and be able to see something with more sensitivity. Then we'll show you what resolution is. So this is some kind of object. I could tease you and tell you it's astronomical, but I won't. But I want you to just see if you can figure out what it is. And I'm guessing you can't. So I'm going to give you a few more photons. And I'll bet you didn't think we were going there. But that illustrates the importance of sensitivity. And this difference gives you a sense of what a factor of 100 in sensitivity will do. This slide shows you that no matter how many more photons I gave you, you will never be able to figure out what it is you're looking at unless I make the image sharper. So here again, I'm guessing you have no idea what you're looking at, but if I give you a little bit better resolution, you realize that to study these objects, you need to be able to separate them from their background as well as from each other. So now I'm going to give you an example in the sky that's a combination of sensitivity and resolution improvement. This first image is taken with about a 1 meter telescope at the Palomar Observatory in California. When I hit return, you're going to see what the same object looks like observed by the Hubble Space Telescope, a 2.5 meter telescope. So that's those two effects together. And from HST, the resolution is limited only by the quantum mechanical interaction of photons with the primary mirror. We call that the diffraction limit of the telescope, and it gets better with increasing diameter. So as the size of the telescope gets bigger, the diffraction limit of the telescope gets better. So one way we can see that is with two telescopes in space, and we happen to have a new one. We happen to have JWST. So if we look at this image taken with the Hubble, a 2.5 meter telescope, we should see a much sharper, much more sensitive image if we compare the same area of the sky to something observed with JWST. And indeed, we do. So that's JWST, a 2.5 times bigger diameter means 7 times the collecting area, making it more sensitive than HST, but also 2.5 times better resolution, focuses the light down into and better separates different regions from each other. So you get the benefit of not just sensitivity and resolution separately, but the combined makes for a much more effective sensitivity than just the collecting area alone. But JWST is the largest telescope that we'll be able to launch for a very long time, not just because we need more money, but because it takes a lot of technology development to figure out how to actually get to a larger diffraction limit, a larger diameter telescope, and support it properly in space. So how do we do better? We're going to have to make bigger telescopes on the ground. And this image illustrates the challenge of getting to the diffraction limit from the ground, namely atmospheric turbulence. So atmospheric turbulence is exactly the same effect as what you see when you look over a hot road. That twinkling, the motion is the turbulence. As hot air is coming off the road, that exact same effect is what we're looking through when we look through the atmosphere up at stars in the sky. So I don't want to keep you in suspense. We do know how to beat atmospheric turbulence, and we do that using a technique called adaptive optics. And I'll show you what we'll be able to do with adaptive optics on GMT. So if that image on the right is an image of an area of the sky, a star cluster taken from the ground, so no matter what telescope you use, with a limiting resolution that's dictated by the turbulence in the atmosphere, we can compare that to what you get with HST. That's a 2.5 meter in space, we see here. So now JWST, the diffraction limit of a 2.5 times bigger mirror than the Hubble. And now here's what we'll get with GMT, a 10 times better limit than the Hubble Space Telescope, a 4 times better limit than JWST, and more than 100 times the sensitivity of JWST, because the combination of the ability to concentrate light in addition to correcting more light gives you much greater overall sensitivity. All right, so how are we going to do adaptive optics with GMT? This is the first generation of telescopes that's being planned from the start to do adaptive optics. Telescopes on the ground already do adaptive optics, so we know that it works. But those adaptive optics systems tend to have been added later, and that means that the telescopes themselves weren't really designed to enable the full capabilities, and they've always been a challenge. So this is the first these are the first telescopes that have been designed to work with adaptive optics from day one. And at the heart of our adaptive optics system is the secondary mirror, which you see up at the top there, floating above the primary mirror, suspended by that or supported by that tripod structure. And in order to, what I'm going to show you now is how light travels through the telescope system. So first light, we'll do that again. First light comes to the primary mirror segments. Oh, I went backwards. Okay, so light comes to the primary mirror segments, goes up to the secondaries, and it actually comes to a focus before the secondary mirrors. That's actually important for how the adaptive optics works, but we won't get into it here. Then it diverges again up and gets caught by the primary mirror, by the secondary mirrors, and then reflected back down to the focus of the telescope. So you get a better picture of those adaptive secondary mirrors here. There are 7 of them, and they're paired 1-to-1 with the primary mirrors. They're about 1 meter in diameter, and they're deformable mirrors, meaning they change shape on their surface 1,000 times per second with a shape accuracy of 50 nanometers. So by moving that rapidly, they can actually take out the effect of turbulence in the atmosphere by adopting the opposite shape of the wavefront as it's coming through the atmosphere, so that when it's reflected, it becomes perfectly corrected. This is a picture of a previous generation of adaptive secondary mirrors. This one is actually used in Chile. And the adaptive surface itself is shown on the bottom there, where I'm pointing with the yellow arrow. The mirror is about 1 millimeter thick, and what you're looking at is it resting on a pad of some kind of foam. On the back of that mirror are magnets that attach it to the actuators that you see at the top. And the actuators are move the mirror against a reference body so that you have something very still against which to push. In addition to the light collecting power of the telescope and the ability to do adaptive optics to correct the atmosphere, you need instruments. And so what you see here is the location in the telescope where the instruments are mounted. Here gives you a much better view. That is where we hold large cameras and spectrographs that will be able to analyze the light and record it for scientific measurements. So you can think of cameras or spectrograph, you can think of that as an instrument that has the complexity of your cell phone, but these are about the size of shipping containers on end. So you can see the structures in the center there. Those are about 3 meters by 2 meters by 2 meters. So actually the design of the telescope is what dictates what instruments you can build and what capabilities you can have for analyzing, dispersing, and measuring the light. And GMT has been designed to enable everything from the optical to the infrared and very wide field instruments that can take spectra of many objects at once, in addition to cameras and spectrographs that can get to that highest resolution to study single objects at one time. And that range of the kinds of data that we can take is critical for science, because all of those different modes enable us to do different kinds of science. So let's talk about some of the things that GMT will be able to do. Okay, this is a close-up of an image taken with Hubble. It's called the Hubble Ultra Deep Field. And this image lets you see objects that are about 1 million times fainter than what you can see with the naked eye. The faintest objects here are about 1% of the brightness of the night sky. And you can see a wide range of objects here. The faintest of those, some of them look faint because they're actually intrinsically faint, meaning they don't contain many stars. They're almost all galaxies. There's only one star that you can see in this. It's the bright object in the center with spikes. Everything else is a galaxy. So the ones that appear faint might be intrinsically faint, meaning they don't actually have many stars in them. And others might be faint because they're intrinsically bright, but very distant. And that's what we mean when they say this is a deep image. It contains some of the most distant objects we've ever detected. When I hit return again, I'm going to just point out and then show you a close-up of some of the most distant objects in this galaxy. These are over 13 billion light years away, which means that the photons we're receiving from them have been, which of course travel at the speed of light, have been traveling for 13 billion years. So we're looking back in time when we detect galaxies that are this distant. And by looking back in time, we're actually looking at baby pictures of galaxies. We're looking at the galaxies right after they formed in the very early universe. So they appear red, not by coincidence, but because as the universe expands, the light is Doppler shifted, just like the sound a car makes as it goes by you. And as light is Doppler shifted, it becomes redder. And so these most distant objects are always red. This is an image taken with JWST, which is even better at finding those distant galaxies because it is more sensitive at red light. So that galaxy that you see here is estimated by JWST's early science teams to be that we are seeing it now at about 300 million years after the Big Bang. Only 300 million years after the Big Bang. That is incredibly rapid galaxy formation. And in order to understand how that galaxy formed, we're going to need to study it in much more detail to know its chemical composition, to measure its internal kinematics, to understand how it's coming together or what kind of processes are going on within it. And in order to do that, you can see that this galaxy is pretty much at the detection limit of JWST. So while JWST will be phenomenal at finding them, if we want to study them in greater detail, we're going to have bigger telescopes to study them at the highest resolutions. So I think it makes sense that we're going to need high resolution, high spatial resolution, very sensitive telescope to study this, but we're also going to need wide fields of view to study objects like this. And the reason for that is not so obvious until you think about the fact that what's being shown there is the sample regions for the deepest JWST pointings so that they can build up a coverage in an area of the sky and look for galaxies like this. And so you can see actually some of those postage stamps, and this is one blow up of one object in one of those exposures taken by JWST. This is the field of view of GMT. So you can see that if we want to be able to study rare objects on the sky efficiently, we need to be able to collect a lot of light from them. But if we can collect a lot of light from many of them at once, we can leverage the effective efficiency of the telescope. It's hard to get a sense of how big a field of view that is, so I'll give you something more familiar. This is what that field of view really represents. It's a 20 arc-minute field of view being compared here to the diameter of the moon. Other telescopes that are operating now and in the two other ELTs have fields of view much more like this, either half to a third the diameter. So both of these things are important. Very high resolution instruments that can take the sharpest images of the smallest objects in one exposure in great detail, and instruments that can essentially multiplex and allow us to study many objects at once. So let's get back to the chemistry and the dynamics question. When we want to study one object at a time, let me give you an example of what we'll be able to see. So this is illustrating the wide field of view. Let's zoom in on one area and start to see some of the galaxies that we might want to study in detail. Looking at what you be able to observe with HST now at optical wavelengths. This shows you what you could observe with GMT. And there's the comparison in one shot. And I'm making this comparison at optical wavelengths because it's at optical wavelengths that many of the atomic transitions take place. In fact, all of the atomic transitions take place. And so it allows us to study much more effectively the individual chemical composition of the galaxy. All right, let's come a little closer to home. So in the last 25 years, we've detected over 5,000 planets just in the nearby, in the area nearby us, in the what we call the solar neighborhood in the galaxy. Even more amazing, hundreds of these are in what we call the habitable zone of their parent star, meaning they're at the right temperature to have liquid water. Based on the numbers that we see nearby, we know that there are about 40 billion planets in the habitable zone around all the stars in the Milky Way. And some fraction of those are the right size and density to be rocky planets like Earth. And so this begs a wide range of questions, so many questions that actually there's a whole new field of astronomy now that wasn't really a field when I was in graduate school, and that's exoplanet science. And some of the most interesting and obvious questions are, how do those planetary systems form, including our own? There are questions about the formation of the solar system and about Earth that we can't learn from studying our own solar system. So studying other planets, other planetary systems is how we'll understand about the formation of the solar system. Also, how common are rocky planets? Do any nearby habitable planets support life? And very importantly, are we sure we'll be able to recognize the signatures of life on another planet? So we're already making a lot of progress on those questions, both from the ground and from space, including by direct imaging, which is astounding. This shows JWST's most recent direct image of an exoplanet. There have been dozens of direct observations of direct imaging of exoplanets using ground-based telescopes as well. Those are very challenging observations, and it's great to see that JWST is succeeding so effectively and is starting to make those observations also. But images like this are not only amazing, they're also very important because they let us measure the temperature and other fundamental characteristics of the planets and their atmospheres. But planets that are bright in the infrared, which is where JWST works, are hot, which means that they're young, right? If something is bright in the infrared, it's hot. So to learn about planetary systems beyond, and planets are only hot soon after they form, they cool over time. And remember, the ones that we're particularly interested in, if we're interested in extrasolar life, are Earth-like planets that have water and are at that perfect temperature to be habitable. Okay, so to learn more about the formation of planetary systems beyond these early stages, and in particular to look at potentially habitable planets, we need to be able to study those planets in reflected light, much shorter wavelengths. That's where GMT becomes incredibly important. So this is an illustration of the sensitivity that GMT will have that will allow you to do that. So this first image shows a coronagraphic image of a planet around a nearby star. So what you're seeing is, if you want to think about how you could observe a planet next to a very bright object like a star, you can think about trying to look at an airplane flying near the sun. You might put your thumb over the sun so that you could see the much fainter airplane next to it. That's exactly what we're doing here. We mask out the bright star so that we can see the much fainter planet next to it. So this is an observation of a planet that's known to be about 10 Jupiter masses. And what you're seeing here is that planet clearly detected, resolved separately from its parent star. But this shows you what GMT would be able to do in this same system. We could easily see the 10 Jupiter mass planet. We could also see much lower mass planets, and that would be much fainter, including much lower mass planets closer in. And this is extremely important because if you can see fainter planets closer in, then the volume within which you can look for planets like this is much greater. And remember, these are very rare objects, so being able to reach more of them increases the likelihood that we'll find interesting planets, particularly planets that might be habitable and also cooler. Okay, so then there's the question of finding signs of life. That requires taking spectra of the atmospheres of these planets. And what we're really looking for is molecules in the right combinations that they can only be produced in the atmosphere by the influence of organic life on that atmosphere, rather than by geological causes. So to do this, we need sensitivity and resolution of GMT paired with the spectrographs that GMT will have. And this beautiful graphic from the JWST team shows one reason why GMT is really key for this, and that is that molecular oxygen is only detectable at optical wavelengths, and molecular oxygen is key as an ingredient in molecules being in the right relative ratios and presence to be from biological as opposed to geological sources. All right, so I hope I've convinced you that we need this telescope. Now I want to show you where we are in the process of building it. So this is the enclosure, which you've now seen before. It's in the final design stage. It'll be complete in late 2023. The final design will be complete in late 2023. And I just want to give you a sense of how what's involved in developing the design of the enclosure. So remember I told you that the louvers that open on the side of the dome allow air to pass through the enclosure. The reason they do that is so that the temperature can be equalized with the outside air, and you can avoid creating any turbulence locally around the telescope. So what you're seeing there is actually the vorticity as air travels through the enclosure. Where it's blue, it's very calm. Where it's red, it's more turbulent. And the analysis for this was done by the Boeing Corporation. So since we tend to fly a lot, we're pretty confident that they got the analysis right. And this was used to help us develop the shape of the enclosure to control wind flow. You can see the telescope structure here. You can see the final, it's nearing completion of the final design. You can see a variety of sort of interesting things in bright blue and sort of light blue. That bright blue and light blue ring around the bottom is the azimuth disk. That rotates like a giant lazy Susan to allow the telescope to point in different directions and 360 degrees. Then you can see the C rings over here in blue. They allow the telescope to dip in altitude, and if they ride on big hydrostatic bearing pads, which you can see right here, that control that motion and help it to be very smooth. So the design of the structure, as I said, will be complete near the end of the year. And the structure is being built for us by a company called Ingersoll Machine Tools in Illinois. In preparation for the fabrication of the telescope, they have built a new assembly facility that has a pit that looks very much like the pier on the summit that you might remember, and that's where they'll do test assemblies of the structure. You can get a close-up view of that and get a sense of the size of that assembly hall from this picture. The adaptive secondaries completed their final design in 2021, and we are now making the first off-axis segment. It's in fabrication. So you see the whole structure that supports those 7 adaptive secondaries on the left, and you see an exploded view of just one adaptive secondary on the right. And I want to call your attention again to what I mentioned before, which is the reference body against which you move very accurately that 1 millimeter faceplate. This is that reference body being fabricated in the lab. This is one of our primary mirror segments. In addition to being beautiful, it's a little confusing what you're looking at here. So let me start by just reminding you that the glass for a mirror is structural. A mirror is reflective because of that super thin layer of aluminum that's applied to the surface. So when we polish the mirror, what we're really doing is polishing bare glass to make it be the right shape. And that's what you're seeing here. So that is an 8.4 meter diameter mirror. And the reason you're seeing honeycomb there is because that structure is light-weighted. So there are honeycomb-shaped holes cut out of the back that helps make it more stiff and much lighter weight. So where you see it black in the middle, there's actually a rib of glass. So where it's black, you're looking all the way through the glass surface into the rib in between the honeycomb structure. Where you see it white, what you're looking at is an air glass surface in the back, and that surface is frosted. So what you're looking at is a very smooth top surface, and it's the back surface that's frosted where the honeycombs are cut away that gives it that appearance. 2 of our mirrors are completely finished and are in storage. A third is in now acceptance testing, but I'm showing it here on the polishing machine that makes it have exactly the right shape and smoothness to plus or minus 50 nanometers. And then you can see over on the right, we have 3 other segments that have already been cast and are still to be polished. They're literally stacking up, so they had to make a rig to store them in the mirror lab at University of Arizona. And we have 2 more to cast. One is the 7th mirror, and then a spare mirror will be cast for use on the telescope so that we can swap them out while they're being cleaned and recoded in use. This is the structure, just to give you a sense of the complexity of the support structure that can support these mirrors while they're pointed anywhere in the sky so that they're held to exactly the same shape. What you're seeing is the cell itself in blue, and then all of those things that are called out are essentially different components that make up the actuators and the thermal control of the mirror, because we want to keep, in order to keep the mirror to exactly the right shape, we can't have any thermal expansion. So we're controlling the thermal expansion and the temperature very carefully. This is a view of the underside of our first test cell in the laboratory where it was being acceptance tested. It passed, of course, so we're moving on, but you can get a sense of the amazing complexity of the mirror cell. As Eric already mentioned in his introduction, we are a partnership of 13 international research institutions and universities formed in 2006. You can see the institutions pointed out there on the map. In the last few years, we have joined forces with our colleagues at the 30-meter telescope project and also with AURA, which is the Association of Universities for Research in Astronomy. We've joined forces with those 2 institutions to form what's called the US ELT partnership. So as US ELT, the 2 observatories would be operating in coordination, and AURA would provide user support and data archiving that would vastly expand the scientific impact of both facilities. Our goal in forming this partnership is to bring the NSF in as a partner in both facilities, and in doing that, make both telescopes available to all the astronomers in the United States. If successful, it would be the largest private-public partnership for research ever undertaken. It would enable much broader participation in astrophysics, which I think is extremely important now in the United States. And it would dramatically broaden the NSF's mission and funding, dramatically broaden the NSF's mission as a funding agency for pure research. And I think that is extremely important, as I've already mentioned, for the continued strength of astronomy and scientific research in the US. So we have the endorsement of the full community, as I already mentioned at the beginning of the talk, and we are extremely optimistic that we're going to get there. So with that, I'm going to end and leave you with this vision for GMT being built and in operation in Chile. And I thank you very much for your interest and for your support for Carnegie.
Thank you so much, Rebecca. That was
My pleasure.
fantastic, incredibly inspirational.
That's what we want.
And we are going to have to
Exactly.
we are going to have questions from from Pigeonhole. First time we've done this. And okay. Like that. I can hold on. Is there anything? Okay, can you hear me? Yes, good. Okay, so the questions are moving around and coming to the top here. The first one, a bit philosophical. Do you think we will find proof of life elsewhere in your lifetime?
You don't even know how old I am.
I wasn't even going to venture a guess.
Maybe I should show you. I'm older than you think. That is a very interesting question. So I think that we will find life. I mean, you could ask, are we talking about bacteria, single-celled organisms, or are we talking about intelligent life? And I think those are really two different questions. I'm extremely confident, actually, that within my lifetime, we will find signs of life on other planets and probably beyond our solar system. Whether we will find signs of intelligent life, that's a little beyond my guess.
And I'm wondering if people were looking at us, what they would say about that question.
Right, maybe we're not intelligent life.
So here's a good one. Will we ever reach a technological wall in astronomy where we can't make better tools? Is there some limit? Are we at an asymptote towards technology here?
I think not. And in fact, I think technology for astrophysics is accelerating at a very rapid pace right now. As I think in a similar way that technology in general, I think we could all agree, is sort of taking off in an extraordinary way. So I don't see an end to it.
So here's two that I can ask in combination. So one is, why are ground-based telescopes important? Why can't we just move to an all-space telescope strategy? And that relates to another question is, would it be possible to build a telescope on the moon?
Okay, so let's start with why are ground-based telescopes important? I think that's a great question, and there's a very real and definitive answer, and that is that ground-based telescopes have always led discovery in astronomy, and they will continue to do so, I think, because we have the ability to, if you think about what you can launch, the technology, even that's on JWST, is about 30 years old. So we planned that experiment, that telescope 30 years ago. It took N years to build, close to 30 years to build. And so what's up there now is extraordinary and 30 years younger than the Hubble, but it is still nothing close to the cutting edge technology that we can use on the ground. So on the ground, we can continuously use better detectors, continuously use better techniques, better technology. And it's really the telescopes are a light bucket, but if you can beat the atmosphere, if you can do adaptive optics, the instruments that you can have on the ground are much, much more sophisticated than what you can have in space. And you can adjust them constantly and react in real time to what you need to learn.
Here's a good geology question for you.
Maybe you can help me.
Are there earthquakes in this area? And what are the backup plans for the worst case scenario?
Okay, this telescope is actually in one of the most seismically active areas of the world. And being in California, I really sympathize. I actually don't have in this talk the seismic isolation system of the telescope, but we have a system that allows the whole telescope structure to break away and essentially roll on roller skates in within a sort of a salad bowl. So it's mounted on structures that can actually move back and forth. And actually, this is the same kind of seismic isolation system that's underneath a few buildings in Pasadena. So I have gone, if you're ever at the Burbank Airport, in fact, you can look at the piers in the parking structure and see these roller skates. They're also, exactly these structures are used under one of the federal buildings in downtown Pasadena. So if you Google it and seismic isolation system, you'll see how we isolate the telescope to protect it from the strongest earthquakes. And in fact, the telescope is supposed to survive a 50-year or a 100-year earthquake. I can't remember, but it will easily survive the small earthquakes, and it has this breakaway system for large ones.
Not built on a volcano, is it? No, just kidding.
God, no,
Um,
that we avoided.
So here's a-
I
here's-
mean, there's a
There's a lot of volcanoes in the area.
there are
Yeah.
volcanoes in Hawaii. Let's
That's a
let's
good
be
point.
clear. There are
That's a good
problems
point.
with that.
Yeah, and that's an active one.
Yeah.
So here's a couple of related questions. Why is temperature often so important to telescope instruments? You hear a lot about JWST being cold. I assume that doesn't mean cold just because it's in space. And a related question is, you mentioned GMT has a complex thermal management system. Is the goal to hold the mirror to a constant temperature or close to air or air temperature, or is it to be cold?
Okay, so let's take the first one of those. So if you're trying to observe in the infrared, what you're looking at is wavelengths where things that are warm have very bright spectra, have a very, very bright emission. So I can think of several movies where somebody defeated a camera that was a security camera that was looking in the infrared by warming up a room. Can you think of some movies like that? So if you have a warm environment, then the background light is very bright, and you can't study faint objects in the infrared. For that, so when we look in the infrared from the ground, we're looking through a warm blanket that is the Earth's atmosphere. By putting JWST in space, and JWST, remember, is designed to work specifically in the infrared, you are putting the telescope itself in a very cold environment, so you reduce the background emission. So it's like the difference, why do we not see stars when we look outside in the daytime? It's because the sky itself is very bright. The faint stars aren't easy to see. When the background light outside in the sky goes down, because the sun is on the other side of the planet, it's very easy to see the faint stars. So that's just the same effect of a warm atmosphere when you're trying to see, or a warm environment when you're trying to look in the infrared. So that's the first question. The second question was about the primary mirror. What we're trying to do is hold the mirror to a very constant shape. So if this part over here was warmer than this part over here, it would expand and it would screw up the shape. So I don't really care what the temperature is. I just want it to be extremely stable. And furthermore, I want there to be no difference in the temperature of the mirror relative to the air. So I want to hold everything very carefully at ambient temperature to minimize turbulence and keep the shape of the mirror. Okay, that was those two.
Questions are moving past very quickly now. So how will GMT measure black holes if light is absorbed by black holes?
Okay, so black holes are detectable by their gravitational field. So black holes aren't nothing. They have mass. They're just mass that's been compressed into such a small space that it becomes impossible for anything to overcome the gravitational force and get away from the surface, including photons. So if there were an object, the mass, if there were a black hole, if the sun were to suddenly turn into a black hole, the planets would still keep moving around in exactly the same way as they are now, because the mass of the sun, the mass of that black hole would be the same. So whether there's a sun there or a black hole there, doesn't matter. It's the mass that affects the gravitational force and the motion of objects around it. So if we want to observe a black hole, we can do it by looking for a gravitational field, by looking for the gravitational influence in the absence of light. So if there's a black hole at the center of our galaxy, we can watch stars moving around the center of the galaxy and infer the mass of some object there by the motion of the stars, in the same way that we inferred the mass of the sun by looking at the motion of the planets. So that's one way. The other thing is that the gravitational field of a black hole will actually affect photons as they're moving by. And so it can act to lens light itself. That's a little trickier to explain, but you can look that one up and get beautiful, there are beautiful graphics that can illustrate how that works.
Okay, just two more questions.
All right.
There's a longer list. But I'm
Okay.
gonna cut it off at 7:30. Optical interferometers are now state of the art. Will GMT be part of any planned interferometry experiments with multiple telescopes?
Not yet. That's not planned yet. That is a great question, though. When you see that happening, it's usually at radio wavelengths where it's much easier to do. If you wanted to do interferometry with optical telescopes, they're usually on the same mountain, and you physically combine the beams. That's a very good question.
And the final question is, when will it be switched on?
In my lifetime. No. Our ascensive first light date is right around 2030 right now, but it depends when we get the complete funding. We are currently engaging with the NSF with the goal of getting funding for construction to begin in earnest on the main structures in early 2025. That would get us to first light in early 2030s.
Can't wait. We'll definitely have you back for
Thank
the
you.
talk of First Light. Let's give Rebecca a big hand.
Thank you.
And thank you all so much for coming. It's been a real pleasure to have you, and we hope to see you again soon. Good night.